Hi, this is Carolyn from nextmv, and today I'd like to show you our decision modeling and optimization tool called HOP. HOP makes it really easy to create, deploy, and iterate on logistics models such as routing, assignment, and scheduling. We'll start with a simple example that I pulled directly out of our user manual. In this system, we're operating a pedicab routing fleet, and this would be a sample of our real-time production data. As you can see, we have 3 drivers, each with a starting location and their own capacity. Some of our drivers can carry 1 passenger, and some of our drivers can carry 2. We also have a set of requests. These are riders that have a pickup location and a drop-off location. Our goal in the model is to create paths for our pedicab drivers to follow. We can do this while minimizing or maximizing any KPI. HOP models take JSON input just like this and produce JSON output. That means they can operate directly on your production data. Whether it's from your data warehouse or directly from microservices, the point is you shouldn't have to translate it to optimize and make good decisions. There are 2 components you need for any model. The first is called a runner, so let's look at that. We're using what's called the command line runner, or CLI runner. A runner is responsible for a few things. The first is reading in the state that HOP is going to operate on and try to optimize. That's the plan data. This is simply that input JSON that we just went over. We're going to do some error checking first and construct a few things for the model as a starting point. Then finally, we're going to return a minimizer, and this is going to minimize whichever value we'd like. HOP can return minimizers, maximizers, or satisfiers. Now let's look at the actual model. Implementing models in HOP means conforming to a certain interface. The first method we need to satisfy is called feasible. This basically says, what is a feasible plan in our operational environment? So for a pedicab routing fleet, it's probably pretty reasonable to say we want to service all of the riders. For this to happen, all of the pickups and all the drop-offs will have to be satisfied. And that's what we're saying here. The second method we need to create is called next. Next is creating all the possible plans for us to go search. It's appending pickups and appending drop-offs to each of the individual drivers to create a set of possible scenarios. Next also satisfies any constraints that we have in our network. So in this particular example, we want to make sure that we don't go over the capacity for any given driver. And that's what we're doing here. Once we have the set of plans to look through, we need some way to compare them. And that's the value function. So we're keeping track of the value over time in HOP and making sure that as we go through all the plans, we're returning the best value. That's the optimal one. So in this particular scenario, we're optimizing for distance, as you can see here. The max distance means that I want to make sure the longest route for all 3 of my drivers is as short as possible. So let's look at this in practice. In HOP, a model is a binary artifact, so it makes it easy to build and deploy as well as ship or test. So the first thing I need to do is go build my model. Cool. So now I actually have a fleet routing model that's just a simple binary. It's going to read that sample data that I showed you earlier from standard in, and it's going to give me a set of solutions in standard out. I'm telling HOP to stream the solutions as it finds them. HOP is going to find improving solutions over time. But we don't want to spend an indefinite amount of time finding solutions. So we're actually going to give HOP a 10-second timeout. This is really nice for production applications, especially in real-time systems with tough SLAs. To HOP, this means give me the best set of routes you can find within 10 seconds, and I'll operate on that. So let's run it. So you can see it's finding solutions as we go. So I'm going to kill that, and we can look at a sample output in the editor. This is what HOP output looks like for that model. Every time it prints a plan, it also prints all the options HOP was run with. So it gives things like the version of HOP and also all the options that were set on the solver itself, as well as anything that we set via the command line. This is really nice for repeatability and testability of your models. This means if you need to go back and triage a particular day, you can actually recreate a decision. So that's all fine and good, but what about the actual solution? So obviously hop also gives the output state, or the solution. And so in this case, the output state looks kind of similar to the input state. We have a set of drivers, and each driver now has a path that it needs to go down, or a backlog. That backlog is a set of pickups and drop-offs in lat longs that sums up to the distance that's on each driver. Finally, there's some stats about the solve itself. So we could have created a simple business logic to create these routes, but instead, by using hop, we were actually able to explore many, many more scenarios. In fact, we explored over 3 million different states. While exploring, we found 6 solutions, and during that 10-second window, our solution actually got better by 18.5%. So that's pretty cool. So let's check out the routes over here. These would be the routes for all 3 drivers, just plotted on a map. So you can see they look pretty reasonable. So now what if we want to go productionalize this model? Well, we could deploy it via the command line runner, but we can actually also deploy via serverless in AWS. That's as simple as switching this from the command line runner to the Lambda runner. Once I save it, you can see that it updates the import as well. So great. Now I would just go build this, and then I can deploy via AWS. Thanks for watching.